Alright, so today we're going to take a look at section 11.3, which is on what's called the Binomial Theorem. And this is going to tie in with what we do in 11.6, which is probability. So there will be a connection between the two sections. So what we're going to do is we're going to look at taking a binomial. We're going to start out with something very simple, like a plus b. We're going to square it. And to do that out, I'm not going to do them all out, but just give you an idea. You've got to multiply a times a times b, another a times b, so that gives you 2ab plus b squared. Right. Now, I'm going to already do out, I have cubed fourth power and I think fifth power. Already did them all out. So that's what you get if you cube it. So that would be like multiplying what you had up here by another a plus b. That's what you get if you do it to the fourth power. And then we'll also look at the fifth power. What I'm interested here is looking for patterns. I want to kind of look at all these and see, is there anything going on here? Because the goal is to be able to do like a plus b to the 50th very easily. Or not even writing out all the terms in a plus b to the 50th, but maybe if I just said, tell me the 7th term, if you did a plus b to the 50th. I'll just ask you for one of them. So they definitely start to expand quite a bit as you keep raising this power. But there's lots of patterns here. So does anybody notice anything about the expansions and maybe some patterns that are in them? Yeah.
Every term contains exponents and they go from highest to lowest, mark the midpoint of the expression, and then they go back to highest.
All right. Can you talk about just the exponent, say on, let's just do one letter. Talk about like on A. What happens there?
Oh no, it's bigger. Fine.
The exponent on A? Let's look at this one, for example.
Okay.
So it starts out as a to the 4th. And then what happens to it?
As you go down to a plus b to the 5th.
Kind of just read like as you go across. So if we just look at this one, just the one that the blue box is around.
Oh.
Like let's look at what happens to the exponent on the A.
The value of the exponent goes down one integer every time.
Yeah. So we have an a to the 4th, then an a to the 3rd, a squared, a to the 1st, and technically the last term you could think of as having a to the 0. Okay, so that's a pattern with the a. What else?
The b is the other way around.
The b is the other way around. So we start out with like b to the 0, and then we go b to the 1, b to the 2, b to the 3, b to the 4. So a and b kind of do the opposite with their exponents. One of them goes up, one of them goes down. What else here? What other patterns do people see? Yeah.
It's like, how do I say it? It's like, never mind. I don't know how to put it in words.
Anyone else notice something? Yeah.
The AB term, squared is 2AB, cubed is 3AB. So that's directly corresponding, and then the B in that is squared to the same level of the original equation minus 1. So in a plus b cubed is 3ab squared.
So which one
Does
are you
that
looking
make
at?
sense?
A plus b
No, the third term in that.
cubed. A times b cubed? No? Which one are you looking
2ab, 3ab squared, 4ab cubed.
at? Okay, so you're looking at these terms. And what was the pattern you noticed in those?
This, the direct multipliers, those things that are coefficient for the.
Okay, so yeah, there is a pattern where one of the terms has a factor that's the same as the exponent. So we have a 5 and a 5, and then a 4 and a 4, 3 and a 3. Now we don't. We did. 2 and a 2. So there is something there. Yep. How about the number of terms in the expansion?
It increases.
There's always
How does it relate to what you're expanding? Yeah.
there's always one more term than the exponent you have.
Yep. There's always one more term in the expansion than the power you're raising to. So that's another pattern. The sum of the exponents always equals the power. So like 5, technically there's a 1 here, so 4 plus 1 is 5, 3 plus 2 is 5, and so on. But, so we could get that part, but the hard part would be, what about these numbers? 1, 5, 10, 10, 5, 1. Where do those numbers come from? Those are not. It's true that those are factors of 5, only because 5 is a prime number. That would happen on any prime power, but it will not happen on 4, because 6 is not a factor of 4. Your numbers here, you've got your 1, 4, 6, 4, and 1.
I mean, I'm noticing that they're like mirroring each other. I don't think that's.
Yeah, there is a pattern there where they kind of like there's a mirror image of them once you get to the middle one. If there is no middle term, then it's like the first 3, then repeat in the opposite order for the last 3. But where are those numbers coming from? We talked about those numbers last week. Those are not just random numbers. We find those numbers in something. In what? The what? They're not Fibonacci numbers. So those, we talked about the thing that I'm thinking of when I mentioned Fibonacci numbers.
Oh, dang.
But what did we talk about with those? Yeah?
Isn't that as you go down, you add them together, they one below them. So like if you look at A plus B raised before it, 1 plus 4, and then below is 5, and then below is 600 is 10.
What was that called? There was a name for that. I remember some kind of triangle.
Like one's point, like you use the diagonal lines.
Yeah, I showed you the Fibonacci numbers on the diagonal. That was a special pattern that comes up in this triangle. We're not going to look at that today. But something else. What is it?
Pascal's triangle.
Pascal's triangle.
Yes.
So here are some of the patterns that you guys noticed. In each expansion, there was one more term than the power you were raising to. I pointed that out. Some of the exponents always adds up to the power. This, I think, was the first one we noticed. The degree on A was going down by 1. Degree on B was going up by 1 each term. But the tricky one, nobody, I don't think anyone noticed this one right away, is where those coefficients were coming from. They're coming from rows in Pascal's triangle. So if you make the triangle, draw that, or not draw it, but if you write that triangle out, you will see the numbers that are in the expansion of those binomials. Now, drawing a triangle is okay, you know, if you only had to do maybe up to like the 7th or 8th power. But if you had to do like a plus b to the 30th, that would require you to know row 30 in this triangle. And while you could figure it out or look it up, there's got to be a better way to get these numbers than getting them from the triangle. But for small values, I would say up to like 5 or 6, 7, it would be okay to use. So the coefficients are coming from Pascal's triangle.
Is there an easier way to find what coefficients it is? Because once it's a very high exponent, you're not going to want to write out everything.
Yeah. Yep, I could tell you. Yep. There's a way to do it. Now, when we use Pascal's triangle, we'll talk a little more about it, but the numbering starts with 0. That's important because if you don't start with 0, it's not going to line up with these expansions. So this would be row 0, that's row 1, that's row 2, that's row 3. So now if you look at raising something to the 3rd power, 1, 3, 3, 1. 3rd power, 1, 3, 3, 1. So this triangle always starts with row 0, column 0.
How do you spell Pascal?
Pascal, P-A-S-C-A-L. So, for example, if you wanted to identify that particular spot, that is row 3, column 1. This is row 3, column 2. That's row 3, column 3. Row 4, column 0, column 1, column 2, column 3, column 4. Okay, so I already kind of did this. So the coefficients are coming from Pascal's triangle. Just make sure you remember that your numbering starts with row 0 and goes up from there. I'll come back to this diagram if we need it to expand something to a higher power. But really, you can make this as big as you want. You just have to keep adding together. You always have 1s on the outside. And each number is the sum of the 2 above it. So 1 plus 3 is 4, 3 plus 3 is 6, 10 plus 5 is 15, and so on. So each row begins and ends with a 1. I just said that. Numbers above it, we add them together. And the numbers in the nth row are the coefficients of the expansion to the nth power. So if I had to expand something to the 5th power, I'd be using 1, 5, 10, 10, 5, 1. Those would be my coefficients. And then I just have to work out the exponents. The A's are going to start at the highest power and go down. The B's are going to start at the lowest power and go up. And then I just kind of write out. They get a little more complicated when you have something like a squared plus 2b to the 4th, but it's still the same basic idea. You're expanding a binomial, but you're going to end up with like a power to a power. So you're going to have to multiply exponents together. But we'll start out with just kind of a basic one, and then we'll do one where the a and the b are a little bit more complicated than just an a and a b. Generally, if I make it a little bit more complicated inside here, I keep the number outside smaller.
So that's the expansion of a plus b to the power of n.
Yep, expansion of a plus b to the power of n. Yep. Okay, so let's try a plus b to the 6th. So first of all, we're going to need the 6th row. So do I have it? 4, 5, yes I do. 1, 6, 15, 20. So 1, 6, 15, 20, 15, 6, 1. Yep, those are the numbers I need. Okay, so how many terms am I going to have when I expand this out? 7. The first coefficient is a 1. A to the what power? 6. And then technically b to the 0. So I'm not going to write b to 0. What's my coefficient on the next term?
It's going to be 6 probably.
6.
And then A to the 5th, and B to the 3rd.
B to the 1st. Okay, and now my next term?
15, A to the 4th, B to the 2nd.
So bring the A down, bring the B up.
20.
So then we have a 20.
And then both are to the 3rd.
Bring the A down, bring the B up. Yep. Okay, what about my next term?
Another 15, except it's from A to the 2nd, B to the 4th.
A to the 2nd, B to the 4th.
And then 6, and it's A to the 1st, and B to the 5th.
Yep.
And then a 1B.
And then 1, which
A to the 0, B to the 6th.
you don't have to put the 1 or the A to the 0, but you can put them, that's fine. But 1B to the 6th. Now what we just did here takes the place of writing A plus B times A plus B 6 times, and then foiling all 6 sets of parentheses together. If you know the pattern, this is a lot faster. But that's what you get if you raise A plus B to the 6th power.
I suppose it's relatively easy, but we have to, are we going to have to like draw out our own Pascal's triangle for reference?
For a small, I'd say up to 6 or 7, you should be able to write it out
Okay.
in under a minute or so. Beyond row like 10, 11, 12, I'm going to give you a way to figure out something quicker. What I might ask you, like if this was A plus B to the, well, you could just use this one, A plus B to the 6th. I would probably ask you to expand the whole thing out like we just did. But another type of question is I could say, just tell me the 3rd term. So like I would just want to know one of them in the whole expansion, just the 3rd. Or I might say, like, tell me the coefficient of the A cubed B cubed term. So you'd have to figure out that it's 20. But it would only be one thing you have to figure out instead of writing them all out. Especially when this number gets real big. All right, let's try this. 2x plus y to the 4th. Now, when you do this one, you want to treat this whole thing like your A, and that is like your B. What are the coefficients in row 4 of Pascal's triangle? 1, 4, 6, 4, 1. Okay, so your first coefficient is a 1 times. Now normally you would put A to the what power? The 4th. But what's my A in this case?
2x.
So it's 2x to the 4th power. And it's y to the 0. What's my next coefficient? 4. And what's going to come inside the parentheses?
2x.
And what power is that raised to?
3rd.
To the 3rd. And what else do I need?
Why is it to the 3rd side?
Because the exponent's dropping down.
Oh, yeah.
What else do I need there?
On the first.
Y to the 1st. Okay, next coefficient. 6. It's always 2x in the parentheses. And the power. 2nd. Power on y. 2. All right. Next coefficient.
4.
4.
1.
2x to the 1st. Y to the 3rd. And my last coefficient. 1. Y to the 4th. Now, this one has a little bit of simplifying we need to deal with. So remember, when you have a factor raised to a power, you raise each, well, I should say, when you have a product raised to a power, you raise each factor to the power separately. So what's 2 to the 4th? 16 times 1.
16.
So that's 16x to the 4th. That's the first one. Now the next one Just following PEMDAS, do my exponents. What's 2 cubed? 8 times 4. 32. X to the third. Y. That's your second term. Third term. 2 to the second power. 4 times 6. 24. X to the second. Y to the second. Yeah, nothing happens with Y. All right. Now we've got 2 to the first times 4. 8. Y to the third. And last term, there's nothing to simplify. So that is what you get. It's a little more complicated than just having an A and a B, but it's still the same idea. And a lot faster, I think, than trying to write 2x plus y 4 times and FOIL it all out.
Yeah, there's so much more room for error. Like, even if you're...
Yeah, when you're FOILing it all out.
It's just so much easier to make mistakes.
Now this one's a little bit more complicated because it's got something different for the A and the B, but it's only to the third power. So what's my third row in Pascal's triangle?
1, 2, 1.
Third row, we're looking for 4 numbers.
1, 3, 3, 1.
Right.
Oh, wait, it's row... Oh, I think I have my thing off.
Okay, so my first coefficient, and what's going to go in parentheses?
3.
To the third. Don't worry about the 2y yet. Or be careful because all the problems we've been doing so far had a plus, a plus. This one has a minus. So it hasn't affected anything yet. But you might want to think of it like this. This is your A. This is your B. A is what comes before the plus sign. B is what comes after. If you think of it like that. So what would my next, well, you tell me, what would my next term be?
3 parentheses 3x squared.
So 3 in parentheses 3x squared. Yep.
Parentheses negative 2y.
Yep. So there's your second term. Okay. What about my third term?
3 open parentheses, 3x close parentheses, open parentheses, negative 2y close parentheses, 2 squared.
And my last term.
It would just be negative 2y squared. Or, yeah, just negative 2.
So I'll put the number in just so we see the 1331. But then you said negative 2y to the what?
3.
Yep. Now remember, when you raise a negative number to an even power, it cancels. Odd power, it doesn't. So let's do this out. So what's my first term going to be?
3x.
Isn't it 27?
Yep, 27
Oh. Oh,
27
x cubed. Now, let's look at what's going to happen here. Is this really going to be a plus or a minus?
It would be a minus.
It's going to end up being a minus.
Because it's all multiplying against the negative.
So what's 3 squared?
27.
Well,
No, 9.
9
Yep.
times 3
27.
times negative 2.
Negative 54.
So negative 54 is your coefficient. And what about my x term?
squared
And my y term?
y.
Y. Okay, the next one. Is it going to end up being a plus or a minus?
Minus.
It's going to be plus. It's
This one's going to be a plus.
Oh, yeah. Because it's squared.
Because what's negative 2 squared?
4,
4 times the 3
12,
times 3 again.
32.
So the coefficient is a 36. What's going to come after that?
36xy squared.
X, y squared. And is the last one going to be a plus or a minus?
Minus
It's going to be a minus. And it's going to be minus y.
8y.
8y cubed.
8y cubed. Yep. There's a few different examples of expanding binomials. Pretty much works like that every time. I would just be careful if you have a minus. I would probably think of it as a plus, so then you can see what your a is and what your b is if you're using the formulas I gave you at the beginning. Any questions on that? We didn't do one with a power to a power. I think I have one. All right, so it's the same 1, 3, 3, 1 again. But you're going to end up with a power to a power. So let me do the expansion, and then I'll ask you guys how to handle the power to a power. So you've got 1 times 2x cubed plus 3 2x squared y squared. And then we've got plus 3. 2x is going to drop to the first power. Y squared is going to go to the second power. And then the last term is going to be 1. The 2x is gone. We don't have that anymore. And now the y squared goes up to the third power. So if you change what's in the parentheses to an a and a b, it will look exactly like what we did before. 1a cubed, 3a squared, b squared. The only difference is what's inside the parentheses now. It's just not an a and a b. Okay, so what am I going to get for my final answer for the first term?
You just say it.
2x cubed.
2 times 2.
No, 8x cubed.
8x cubed. And my second term?
12x squared y squared.
Yep. My third term is going to be what?
Want to be 6x and then y to the 4th.
6x y to the fourth. And my last term?
That one would be
Y to
y
six.
is 6.
Y to the sixth. There you go. So that's the only other type of situation that can come up when you have a power to a power. You got to multiply those exponents together. Okay. Any questions on that? All right. So we've just been figuring out these coefficients again by using what we know about the triangle, because the powers really haven't been that high. Right? So now we'll talk a little bit more about what do we do if the power you're raising to is going to be large. Okay, we need a better way to calculate what we call the binomial coefficients. And again, I didn't say this, hopefully people know the reason it's a binomial is because how many terms are inside parentheses? 2. You're raising 2 terms to a power. There might, I'm not sure, I think there is, but there's also a trinomial expansion. So like if you have a plus b plus c to a power, there is a pattern for that too. I'm not sure if it's connected with Pascal's triangle, but since you have one more term, triangle is like a 2D thing, it might be more like a pyramid of numbers you have to look at. I'm not sure. I'd have to check it out. All right, so in order to figure out these coefficients in a better way, we're going to have to use something called factorials. Does anybody remember ever studying about factorials? Anybody remember the symbol for them? Yeah?
Symbol's an exclamation point.
Yeah.
Factorial is like, well, I mean, the usual one is just like, it's like 1 times 2 times 3 times 4, or, yeah. It's just a sequence of numbers multiply one after another.
Yes, it's kind of like what we've done with sum of numbers, where we add up a bunch of numbers. A factorial is like multiplying a bunch of numbers. Right? And there actually is a symbol, kind of like sigma, that you can use that represents multiply instead of add. We don't get into that. But the idea is that if you have any positive integer, okay, so this does not apply to decimals, this doesn't apply to negative numbers. The symbol for a factorial is an exclamation point. And the way you would pronounce this symbol is N, because it has the exclamation point. So you gotta give it a little, exclamation pointness. Pointness, yes. Exclamation pointness. So n factorial basically means the product of every number from 1 up to that number. So like 6 factorial would mean 1 times 2 times 3 times 4 times 5 times 6. So n factorial is the product of all integers from 1 up to n. Now, the graphing calculator, you can put in decimals, but then weird things start to happen because it doesn't really fit the definition of multiplying integers. So now you start looking at decimals, and it's a little different. I think you can do like 0.5s with a factorial, like 3.5. I don't remember where factorial is. It's under probability.
Why is it under probability?
So you can do 3.5 factorial, but I don't remember if you can do anything besides a 0.5. No, it doesn't let you. So there must be some rule for being able to figure out like a 0.5. I don't know what that rule is, but we don't have to worry about it because we're just going to deal with integers. Well, 0 factorial, that's kind of a weird one because how can you multiply every number from 1 up to your number? 0 is not up, it's down. So that's kind of a special case. There might be an exclamation point. No, I think the quickest way to get to it is under probability. So 0 factorial, that's a special case. It's 1. Now the rest of them we should be able to figure out. What do you think 1 factorial would be?
Also 1.
That is also 1. And then 2 factorial? That's 2. And 3 factorial? 6. And what about 4 and 5 factorial? 24 and 120. So factorials grow very, very quickly. By the time you even get to like 25 factorial, I mean 25 is not really that big of a number. But if you try to multiply 25 factorial, it's already a number that has 25 decimal points. And by the time you get to like 60 or 70 factorial, it's probably going to be too big to do on the calculator. So when we get into calculations that have big factorials, we're going to have to simplify them before we can put them in, because it's very easy to get something that's too big, and then if you put in something that's too big, I think it just says overflow or something like that. Yeah, it's too big. So if you're getting an overflow error, it's because you didn't simplify something before you plugged it in, because none of the problems I give you are too big to do on a calculator.
Are we supposed to do those on the calculator, or kind of just gonna?
You'll see what we're going to do. You probably won't need a calculator for most of them because of what's going to happen.
Yeah, alright.
So let's say we wanted to find a particular number in Pascal's triangle. The goal here is not really to write out the entire row, because that's still going to take a while, even with this shortcut. But maybe I just say, tell me the number that would be in row 12, column 5 of the triangle. Well, first of all, we have a special notation that we're going to use to represent row 12, column 5. The top number is the column. I wrote that up above. And the bottom number is the row. So if you wanted something in like, I don't know, like column 6, row 2, the notation for that would be this. And the way you pronounce that is 6, choose 2, or N, choose R. And the reason you pronounce it that way is because if I had 6 objects, and I said to you, you can pick any 2 that you want. Pretend they're all different. I know some of these are the same. If you have 6 objects, and I said to you, you can pick any 2 that you want, how many different ways can you choose 2 out of these 6 objects? That's getting into probability, and that notation right here will tell you that. So all the numbers in Pascal's triangle actually tell you the number of ways of choosing something out of a group of objects. So like if we go back to it, let's just take a look at it. If I had 4 objects and I said you could choose, let's say, 2 of them. 4 objects, and you're allowed to pick any 2 that you want. That's 4, choose 2. Go to row 4, column 2, and that will tell you how many ways you can pick 2 objects out of a group of 4.
Yeah, no, okay, I was going to ask about that. On the
6.
The note page that you were just on, you had the row and column labels, but I was confused.
Column is always on the top, row is always on the bottom.
Oh, wait, what?
It's because the way you wrote it at the top,
But
it
it's
says
row and column
and
R.
column R. I
Row.
think you switched them by accident.
Yeah.
Oh yeah, let me fix that. Row. Yeah, you're right. I did switch them. Thank you. That's important.
Okay, I was, alright.
Yeah, I was gonna say, how can you say like 4 choose 5?
Yeah, you can't choose more than you have. So yeah, row is on the top, column is on the bottom. Sorry about that. So row is N. Now column is on the other line. But row is the N, column is the R. Any question on that now?
Can you go back to the triangle for a bit?
Yep.
So you could say 4 choose 5.
Row. So remember, you start with column 0.
Oh,
So yeah. So if you had row 4, it would represent having, say, 4 objects. How many ways can you choose 2 objects out of 4? 0, 1, 2. There are 6 ways. You could pick A and B, B and C, C and D. You could do A and C, A and D, and B and D, I think. Those would be the 6 ways. B and D and D and B are the same. So when we're talking about choosing something, order doesn't matter. If you get to go home with a red and a black, or you go home with a black and a red, you're still going home with a red and a black, or a black and red. It's the same. Alright, so that's what this triangle really tells you. The number of ways you can choose objects out of a group of them. So remember, when you are doing the numbering, you do have to start with row 0, column 0, or things won't line up correctly. So we're not going to go through the proof of this formula, but I'm going to give you a formula to calculate row 6, column 2.
Oh, that's handy.
So I'm going to give you the formula that does that. We can look up the answer because I think I have it. What's row 6, column 2? For this number?
That's column.
That's column.
That's column 1.
You're testing this one.
I was just testing it, yes. 5, 6, 0, 1, 2. So the answer should be 15. Right? For 6, choose 2. So let's see when I give you the formula if it works for 6 choose 2. So that's the formula. N factorial. So it's 6 factorial divided by 6 minus 2 factorial. 2 factorial.
So much to say.
Now, when we do that, we could simplify it quite a bit. Because what does the top mean when you write 6 factorial?
Every number multiplied up just between 1 and 6.
So 6, 5, 4, 3, 2. And what's 6 minus 2?
4.
And what is 4 factorial if you write it out?
4 times 3 times 2 times
4 times 3 times 2. And now times what's 2 factorial?
2.
It's just 2. So you have a 4, 3, 2 and a 4, 3, 2.
Oh, interesting.
And 2 goes into itself once and goes into 6 3 times. Whenever you calculate a factorial, the entire bottom should always be 1 because you cannot get decimals. The number of ways you can choose something is always an integer. So what do you get for an answer here? 15. And was that the number we circled on the triangle?
Yeah.
So now we have a way to calculate a number in Pascal's triangle. So in the triangle, what would be the very top spot? That would be row what, column what?
0.
Row, not row 1, column 1. Nope.
No, it's row 0, column 0.
Row 0, column 0. And then what would be the next spot right there?
Row 1, column 0.
Row 1, column 0, and this one?
Row 1, column 1.
Row 1, column 1. And you can write the whole triangle this way, in this notation. This is row 2, column 0, row 2, column 1, row 2, column 2. So now I've rewritten the entire triangle using a notation that you have a formula for, where the top number is the row, and the bottom number is the column. Row, column. So now you can calculate any spot in the triangle that you want to know. You want to know what's in row 15, column 7? Well, just use the formula where n is 15 and r is 7, and do it out with the factorials. And so we'll try doing out one more of those factorial kind of problems, and then we'll stop. Let's see. Put it on this page. This one. All right. Let's try 6 choose 4. This is n. This is r. And remember your formula. Right, so what would go in the top?
6, 5, 4, 3, 2, all times.
Yeah, and I'm just going to do 6 factorial, and we'll do all the canceling when we rewrite it. But yeah, so 6 factorial over what would be here,
6 minus 4.
which is
Oh, not 2.
2,
And then
yep, 2 factorial,
and then 4 factorial.
and then 4 factorial. So we're calculating the number in row 6, column 4 of the triangle. Okay, when we do this out, the biggest factorial in the bottom is going to cancel into the top. What would be left when you have 6 factorial if you cancel out the 4 factorial part?
6 times 5.
You're just going to be left with 6 times 5. 4, 3, 2 is gone.
Wait, alright, isn't that the same?
Yeah, we might have done one like this. I think we did 6 choose 2,
Yeah.
but since it's a mirror image, the triangle is symmetric, it's the same answer. What's 2 factorial?
2.
And that gives me 15. And let's finish up with this one. Okay, what goes in the top?
9 factorial.
All right, and then in the bottom?
4 factorial and then 5
Factorial,
factorial.
5 factorial. Okay, so what are you going to be left with in the top if you cancel the biggest factorial that's in the bottom into the top?
9 times 8, 776.
So 9, 8, 7, 6. 5, 4, 3, 2 is going to cancel this 5, 4, 3, 2. And 4 factorial, 4, 3, 2. Now you can cancel however you want, but everything in the bottom should divide into everything in the top.
Then 4 and 2 cancel the 8.
So yeah, I was thinking 3 times 2 cancels the 6, but same thing. So 4 times 2 cancels the 8. And 3 goes into 6 how many times? Twice. So you should be left with a relatively small calculation. What's 9 times 7? 63. Doubled.
26.
26. Now that's not a row of Pascal's triangle we've gone up to, so we can't easily check it, but I'm pretty sure that that is correct. Any question on that? All right, so yeah, we were at the last page. We'll have to finish it next time. But the last problem is going to be to take an expansion and figure out just one term of it. I know it's going to have 16 terms. All I want to do is know the 12th. So with what I've taught you, you should be able to figure it out. You should be able to get the coefficient from the triangle. This is row 15, column 12. That's the number you need. Then you just have to work out your powers. Think about, okay, it's going to start as 2x to the 15th, and 2x to the 14th, 13th, 12th, 11th. So you just have to kind of figure out your powers on the x and the y. Right, but we'll start with that next time, and we can go over how to do that. Okay, so those are the problems for tonight. The 21 to 25, that does have one like the one we just mentioned. So if you get stuck on that one, that's okay. We'll go over it in class. But I think some people might be able to get it.